radio frequency identification. It's used a lot in like passports, library books, pet implants if you want to, hold the medical history. That's probably the political video that she goes into is, what if we put RFID chips in ourselves?
We should.
We should. Why not?
Get lost.
But the RFID I will be talking about is EPC. It's electronic product code. It was really popularized by Walmart. And the reason why they really use it is that it's a short-range network. It can work over 10 meters, actually. And it works whenever the tag's not visible. So if you have, a whole bunch of clothes in Walmart, I guess, you can scan all of them without actually seeing them, which is really nice. And it's used as a barcode replacement, those little stickers, since it is a sticker in itself. And they're trying to make it more of a cheap alternative, and they're pushing retailers towards using RFID chips by requiring their top 100 suppliers to use RFID in all of their transactions they do with Walmart. So it then goes down the chain to smaller retailers. How it works, it's a low power system using readers and tags. The reader is the intelligence system of this network. It pretty much supplies all the orders and even the power for the tag. This is done, sorry. Oh, I'm getting ahead of myself. All right, so whenever the tag gets information, it can either absorb the signal or bounce it back to the reader using the power that the reader sent over. And what the big thing about sorry, I'm just getting all scattered for a second. The reader always transmits a signal, and that signal is what powers the tags. What the tag uses is something called backscattering, which probably been on test. Backscattering. What it'll do, it can switch either from reading the signal it gets from the reader, or it can reflect the signal with the data that it gives. And the way that it does that is the reader will send an empty packet that just has power in order to receive the data. And I'll go into how it translates that data in a second. But the way the signals are translated on the, is it alright if I erase this?
Yeah, go ahead.
Is that the right kind of marker though?
The way that it works, whenever it sends one of these signals, it first takes the reader signal and it determines what kind of bit it is by how long the low power lasts. So say if it goes like that, that could be a 0 from the reader, but if it's a longer low power signal, that could be a 1. And the way that when I'm talking about backscattering is that it will then, the tag will then take the pulses. Well then instead of reading these dips, it sends pulses like this kind of thing, to where the delay is what determines what kind of bit it is, so that would be a 0. And then if it's a longer delay between the pulse, the reader knows that's a 1. That's what's backtracking. And then to establish a connection, kind of works like a slotted aloha, where the reader first broadcasts its queries to the RFID tags. And the slot number, the number of slots can change dynamically depending on how many RFID tags are around. The tags respond to a random slot to prevent a collision. And at first, whenever the RFID responds back to the reader at a random slot, it first sends a 16-bit key just to pretty much say, hey, are you empty? And then it goes back and says, okay, I'm empty, or it's full and you got to move on. Whatever it does, this right here, say this one RFID tag, it then stops transmitting and waits for all the other RFID tags to synchronize with the reader before then transmitting its data across. The reason why it sends a 16-bit signal is because since it's such like a low power connection, you really want to preserve as much power as possible. And if you were to send this EPC identifier anywhere to collide, you're just, it's 96 bits instead of 16, so it just really preserves the power. Let's see, and then once the reader knows what the tags are, it can then operate on them accordingly. It can read the data from the tags. It can take a subset of tags, so say if there's white jeans for whatever reason you want those or something, you can then take that subset. The reader can also write on the tag, so if you want shipment information from tracking, you can put those on the tags themselves. The tag, since it's a low-powered system, so you're trying to be as efficient as possible, and all the intelligence is on the reader. The reader knows what kind of information that it wants from the tag. So all the tag needs to do is send what data it needs to back. There's no headers, no real information. It's a real bare bones kind of thing. This is a message format. This message is specifically one of the query messages. You can see it's small. I think the bits add up to 22 bits. Whenever it sends a message, you have the command to start it, the physical parameters, which set the transfer and response rate from tag to reader. Between, I think it's 12 and 25 kilobytes a second, so it's slow. And then we have this tag selection where you can then, it selects a subset of tags, and you can also allow the tags to be connected to multiple readers at once. So it can just be used in different data collection types. So, a jacket can be in winter wear and rain wear kind of thing, in Walmart's case. And then the queue defines how many slots there are from 0 to 2 to the queue minus 1. And that's what also changes dynamically. It can get bigger and smaller depending on how many tags are in the area. And then there's the CRC, which is the cyclic redundancy check, and that's just for error detection. It can be as small as, I think, 3 bits, and it can be as big as 10, depending on how you want the errors to be checked. All right, and that's RFID. So I guess I got questions. Where do the tags draw their power from?
The reader.
The reader. That is correct. You need a pen. All right. And what's the method called whenever the tag sends signals back to the reader?
Backscattering.
That is backscattering. That is RFID. Does anyone have any questions about RFID before we move on? No?
I actually have a video before we move on to the next section.